to 5.06. So we're going to build on what we did yesterday and talk briefly about the day before. What I would encourage you to do is on your own complete the YouTube explosion task that we worked on in class. We're not going to give it any more time in class because I only allotted one day for it. But I would encourage you to work on it on your own, and of course stop by office hours on your free time to talk about it, and we can go over some of the solutions. It would probably make kind of this whole idea of a geometric series and a partial sum a little bit more intuitive. All right, here we go. Start off with, we're going to take a look back at the chessboard inventor problem. So remember, the chessboard inventor invents the chessboard, takes it to the king, says, check out this chessboard. King is so impressed that he says, anything you want in the whole kingdom, it's yours. So he says, okay, here's what I want. I want you to put 1 grain of rice on the first square, and I want you to double the number of grains of rice in each successive square. So the next square will have 2, the next square will be double 2, which will be 4, and the next square will be double 4, which is 8. We could keep going to 16, so on and so forth. And the inventor asked that he do that and that he be able to keep that much rice. So the king says, of course, sure, that he doesn't think about the math, says, okay, whatever you want, and gets blindsided by the fact that this is a lot of rice. So if we think about the amount of rice that the inventor is going to get, what we do is we start adding up all the squares. So we're going to start with 1, and then we're going to add the next square, which is twice that, which is 2, and the next square, which is twice that, which is 4, and the next square, which is twice that, which is 8. And what we really are dealing with is a geometric sequence, right? So the first term is going to be 2 to the 0. The next term that we're adding is 2 to the 1. The next term that we're adding is 2 squared. And if we think about the squares, right, this is square 1, square 2, square 3, square 4. Square 4 is going to be adding another 2 to the 3rd, which is 8. And if we were to go all the way out to the 63rd square, the 64th square, I guess I kind of gave it away there. If we go to the 64th square, what's the exponent going to be? Well, starting with 1, that was 2 to the 0, 2 to the 1, 2 to the 2nd, 2 to the 3rd, and we see that when we get all the way to the end, we're going to be adding up, and the final term is going to be 2 to the 63rd. Right? So this is going to be the total amount of rice that the inventor gets. And the reason that we're going to use this example is because I bet you don't want to go on your calculator and type in 2 to the 63rd plus 2 to the 62nd, so on and so forth, all the way down the line. And so what we're going to do is we're going to look for a more simplistic, more efficient way to compute this sum. Now, before we move on, I want to mention that this is a partial sum of a geometric series. A geometric series is where I'm adding the different terms of a geometric sequence. So term 1 would be 2 to the 0, which is 1. Term 2 would be 2 to the 1. Term 3 would be 2 to the 2, right? Term 4 would be 2 to the 3. And a geometric series is saying, okay, add up all the terms. A partial sum is when I add up all the terms to a certain point. Okay? So don't worry about that too much right now. We'll define it in a second. What we're going to do is sort of think about how can we represent this in an easy to work with way so that we can compute this easily. All right. Now, here's the sum that we're going to try and compute. And you'll hear me say the word sum, and a sum is just repeated addition. So this is a sum because I'm adding these different terms together. And of course, this is the partial sum if I had these 64 squares here. And what I'm going to do is a couple of really tricky mathematical, I guess you just call them tricks. And to say that they're tricks is kind of deceiving because they're completely logical and sound, and what they allow us to do is rewrite things like this in a much easier to compute fashion. Okay, so I'm going to make use of a simple idea, something that you've done before, which is I can multiply anything by 1 and it will remain the same, right? So if I were to multiply this whole thing by 1, it would stay the same. Now, you'll also know that 1 can be written as a fraction where the numerator and denominator are the same thing. As a concrete example, right, you know that 5 over 5 is 1, right? So if I were to multiply this whole thing by 5 over 5, that's the same as multiplying by 1, and I'll be maintaining the same quantity, right? Multiplying by 5 over 5 would not change the overall quantity here. So what I'm going to do is I'm going to multiply by the fraction 2 minus 1 over 2 minus 1. And I'm going to write the 2 minus 1 in the denominator as dividing the whole thing, right? Because when I multiply this by a fraction, I multiply everything by the numerator and then divide by the denominator, right? Now, notice 2 minus 1 is just 1, right? But I've written this specifically as 2 minus 1 for a reason, okay? And what we're going to do here is we're going to FOIL when we multiply these out, and we're going to notice that we get something pretty easy and pretty wonderful, okay? So if you don't understand how this is legal, I want you to pause the video and re-watch that. Okay? Remember, 2 minus 1 over 2 minus 1, this is 1. So I'm multiplying this whole sum here by 1, which means whatever I get is going to be the same thing as this original piece here. Okay? So whatever I get is going to be equivalent. And now what I'm going to do is I'm going to go through and I'm going to multiply. Okay? So let's start by multiplying, talking about how we would FOIL this. So I'd have to multiply 2 by every single thing in this piece here, this expression here, and then I'm going to have to multiply -1 by every piece in this expression here, and I'm going to combine like terms. So let's begin by first multiplying -1 by the first term in this expression. So I'm going to try and keep track of all the multiplications that I'm doing, and let's start here. So I'm going to have -1 times 1, which is -1. Okay? Now let's multiply 2 times the first term, and notice that I'm going to get +2. Okay? Now let's multiply -1 by the second term, and we're going to get -2. Okay? Now, I want you to make sure that you understand how this is legal, right? FOILing out simply means multiplying each piece of my expression by every piece in the expression I'm multiplying by. So if I want to multiply this by this, I have to multiply each piece of this expression by each piece of this expression, and then add it to the multiplication of this piece times each piece of this expression. Okay? So I'm just going to go through and I'm going to do that, and I'm choosing it in an order because does it matter the order in which I add and subtract? It doesn't, right? If I add 4 plus 3 plus 2, I could do 2 plus 3 plus 4. It doesn't matter the order. So now I'm going to multiply 2 times the second term here, and I'm going to get 2 times 2 to the first, which is going to be 2 to the second, right? 2 times 2 is 2 squared, or 4, and I'm going to write it as 2 squared. Next, I'm going to multiply -1 by 2 squared. And a negative times a positive is going to be negative. So this is going to be negative, and 1 times anything is that something, 2 squared. You might be seeing the pattern here. Okay? So what I want you to do is pause the video right now and look at this, what we have so far, and see if you notice what's happening. What you should notice is that there are terms which are going to be canceling out. So +2 minus 2 is just going to be 0. 2 squared minus 2 squared is just going to be 0. Nothing crazy there, okay? And this pattern is going to continue, right? Whenever I multiply 2 by some term here, when I multiply -1 by the term after it, I'm going to cancel those out. So as an example, concretely, 2 times 2 to the first power was 2 to the second power, and then -1 times 2 squared is going to be -2 squared, and so those two are going to cancel. So let's keep moving down the line. Let's think about, we know that everything is going to cancel, and let's think about what happens when we get to the end. So getting to the end, I'm going to take 2, and I'm going to multiply it by 2 to the 62nd power. Okay, so I'm going to go ... I know everything is canceling out to 0 along the way. So 2 to the 62nd power, 2 times 2 to the 62nd power, that's going to be 2 to the 63rd power. Right? And then -1 times the very last term is going to be -2 to the 63rd power. And those, of course, are going to add up to 0. Now notice, I've multiplied almost everything, okay? I've multiplied -1 by everything, right? I've gone from the first to the last. I've multiplied 2 by almost everything. I multiplied by the first term, second term, third term, all the way to the second to last term. The only one I haven't multiplied it by yet is the very last term. So let's multiply by 2 on the very last term, and that's going to give me positive 2 to the 64th power. Okay? All divided by 2 minus 1. Okay? Now, if you're a little hazy on how that worked out, rewind the video, watch it over. Okay? I'm simply distributing out and multiplying and then adding the terms that are canceling. So what do I have left over in the numerator? Well, this went away, everything else is canceling all the way up to the 2 to the 63rds, and the only thing I have left over is -1 plus 2 to the 64th power. So what I'm left with in the numerator is 2 to the 64th power minus 1, all divided by 2 minus 1. What's 2 minus 1? That's just 1, right? I'll write it here, 2 minus 1. This is much easier, right? This I could compute much more easily because I can take 2 to the 64th power. Wolfram alpha can, at least. Okay? So this we could compute. So what I want you to do right now is I want you to go to Wolfram alpha and I want you to compute this. Okay, so pause the video and come back. All right, so when I type this in, I'm probably pretty surprised to find out that the answer that I get, and of course remember that 2 minus 1, the denominator is just 1. So this is really just boiling down to 2 to the 64th minus 1. And I'm going to get 18 quintillion, 446 quadrillion, 744 trillion, so on and so forth. So the way I would write this, I would probably use an approximation here. So this is approximately 18 quintillion. 18 zeros. Okay. And that would be the number of grains of rice grains, that our inventor friend is going to get, which is quite a bit of rice. And also is a lot easier to find than adding all of these up. And you could try it out. If you added all of these up, I encourage you to do so. You'll get the exact same thing as if you do 2 to the 64th and then subtract 1. Okay, so that was a great example, and now what we're going to do is we're going to talk about this in a general sense, so for any geometric sequence, and we're going to find that we can compute the sum, the partial sum, without much trouble. So let's reintroduce just a couple of things. A geometric sequence, of course, is a sequence where each term is multiplied by a constant ratio, right? So starting with the first term, I would multiply by that constant ratio a certain number of times to get to the nth term. Okay, so this is the definition of it. And then a geometric series is just going to be the sum of all the terms in a geometric sequence. This is a geometric sequence, okay? So the geometric series would be adding up a sub 1 plus a sub 2 plus all the way out onto infinity, okay? Now obviously we're not going to be able to add them quite yet up to infinity, so we take what's called a partial sum. So the partial sum, and we denote it as S sub n of a series, is the sum of the first n terms, right? So S sub n means you go up to n terms of the series. So what I mean by that is that S sub n is going to be equal to the sum of the first n terms. So I'm going to start with term 1 in my sequence, go to term 2, all the way up until I get to the last term, a sub n. And we saw this is just like the chessboard, right? I'm starting with the first term and going all the way up into a certain term. Of course, we went up to the 64th term in our example. Okay, I'm going to introduce some more notation here, which is called sum notation, and it tells me to sum things or add them. So another way of writing S sub n, or the partial sum, is to say take the sum. And so this is the Greek letter sigma, and this means to take the sum of all the things that are included in it. So what I want to do is I want to take the sum of all the terms. So whatever the term is, I'm adding it. So what I'm going to do is I'm going to say, let's start. We're going to have to use a counter. We're going to start with 1. So we're going to use I as our counter. So this says start when I is 1 and go all the way up until I is n. And what you're going to be doing each time is you're going to start when I is 1, and that's going to say take the first term. So you're going to start with a sub I. So the way that we'd work through this is that we say, okay, start when I is 1. So that's going to be a sub 1. Then you're going to add to it what you get when you change I to 2. So I is going to increase. It's going to go 1, 2, 3, 4, all the way up till it gets to n. So what this really does, it's the same thing as we have up here. It just says start, go a sub 1, add it to a sub 2, add it all the way to everything, each thing in the middle, all the way till you get to a sub n. So this is another way of writing repeated addition of terms, okay? And what we're going to do here is in class, we are going to derive the formula for finding the partial sum, okay? So we are actually going to be able to say, okay, instead of having to add them all up, there's a way which we can just compute it right off the bat. So the last thing that we want to do is we want to remember that each of these terms is a geometric term, okay? So we can actually go ahead and compute, we can write this more formally, we can say S sub n is going to be the first term, right, which is a sub 1 r to the 0 plus a sub 1 r to the 1 plus all the way out until I get to the last term, which is going to be a sub 1 r to the n minus 1, right? These are just each of the geometric terms in our sequence, okay? And I could write this using summation notation. I encourage you to go ahead and try doing that. We'll talk about it at the beginning of class, and then we're going to actually derive how to compute this and apply it to some easy to work with series. Okay, but that was a lot for now. Make sure that you have a comment, a question, so that we can get ready and be productive in class tomorrow.